Okay. Here's my deal with notes. I'm not a firm believer in writing everything down. You were probably taught at a young age, when the teacher writes something on the board of the screen, you're supposed to write word for word everything down, right? I'm trying to train people not to do that. Because the university professor is not going to wait for you to write every word down. They're not even going to not write every word down. And every once in a while they're going to be lecturing, which is what they call it. And then every once in a while they'll go and write a key term on the board. And they'll expect you to pick up something or other as they're just talking away like this, and you have to write it down. They're not going to write it down for you. It's a skill you're going to have to learn. I learned it the hard way. I hope that I get you to that point where you're not going to have to learn it the hard way. You're just going to have to, oh yeah, I can do that. Okay? So please don't feel like you have to write word for word everything that's up there. Because not only do I record the video, but when I'm all done, I do this, and I go export, PDF, and guess where I put it? Post to Schoology. So if you think you're going to learn better by sitting back and just watching, and then printing out the notes later, that works. You do that. If you're just lazy, and you don't want to write notes, and you say you're going to print it out, but then you don't, well, then you're just cheating yourself, and that's not going to work so well, right? But you do what you need to do to make yourself, or make best for you, to learn what I'm talking about here. Okay? So I'll be reminding you of that every once in a while. I know there's 2 or 3 people in the room that will feel like they have to write every single word down because that's the way they've been trained. I get that. But I'm going to start encouraging you to not. Okay. I don't know where that link goes. I hate that. What is physics? What are you going to learn here? Honestly? Yeah, come on. Describe. What are you going to do for the next 5 months? Graphing? For a second, I just said crafting. We're in trouble. Anna, what are you going to do in here? I'm going to get rid of this hoodie. It's too hot. You're taking physics, and Granny says to you, Jason, what are you doing in school this year? And you say, I'm taking physics, Grandma. What physics? How do you explain it to Grandma? That's the way I like to talk. How do you explain it to Grandma? Come on, what do you think? Don't know?
I'll send her a link to Schoology.
Oh, she's good answer. One of these years, I'm going to have this memorized. Well done, Jason. You'll hit record. Yeah, you're going to need like ruler skills. What would you really call ruler skills? Measurement skills, experimentation, trying things out. There will be experiments where you fail, if you will, and you're going to have to try it again. Analysis skills, which deals with graphing. Basic mathematical knowledge and skills. Adding, subtracting, multiplying, dividing. Maybe a little bit of creativity. What else? Some graphing skills we're going to review today. Estimation. We did a little bit of that yesterday when we were talking about the number of loads of laundry. We did some estimation, right? These all play into this. You might not realize it. Maybe some patience. Why do you need patience? I need to be reminded to have patience. I need to be reminded, please do, that you haven't really taken physics yet. Because I have to go back to every semester, I have to go. It's like, have you seen the Bill Murray movie Groundhog Day? Have you seen that? Every day is the same. Every 5 months it's the same for me. I need to be reminded of that they don't have, you guys don't have the skills. Remind me. I need to be patient. You need to be patient. When do you need to be patient, do you think? Do you? You're in lab today? Explain. That's true. Work with someone else, right? Be patient there. Okay, that's good. I was thinking more about like you're having trouble to begin with, right? Are you going to struggle in some cases? Absolutely. Be patient. You're probably, many of you, used to getting good marks without really trying very hard, right? Give me the nod. I get a few. I get a few of these too. I look for those, by the way, right? If I'm asking a question, it's okay to give me this or this. If you don't want to answer out loud, just give me this or this. That's all I need, right? Let's try again. Most of you are probably pretty used to getting good marks without working very hard. Okay. Some of you are going to be challenged on that. You might have to work hard, and that's where patience comes in. Oh, who's calling me? It better not be my mom or your mom, man. I don't know who that is. What's the difference between taking high school physics course and studying physics at the university doctorate level. You are taking high school physics. Sheldon is studying, he has his doctorate, he's teaching, but if you're taking your doctorate, what's the difference? And there's one key difference I will admit most kids don't see. But I'll give you guys a chance. What do you think? What's the difference between what we're going to do and what guys like Sheldon and Kuchar Poly, those guys are doing? There's one very fundamental difference. Any ideas? In the back of your textbook, if you have one, there would be stamps. In the back of their textbooks, they're breaking new ground. They're like the person out there breaking trail. The first person to drive down the road in the snowstorm. You guys, trust me, thousands and thousands and thousands and thousands of students have been through what you guys are going to be through, right? Tried and true. I've seen the same problem. I've done the same exact problem for over 20 years. Okay? So that is a huge difference, is that you're just sort of starting out on your path of physics. But real physics, real physics is at the university level where they're actually researching and they don't know the answer. Okay? I used to do a little lab. I'll show you. I'll do a quick version of it. Who wants to volunteer? Yes, surprise. Okay, Jason. This is what's called a black box. You know why? It's black. And it's a box. Tell me what's inside without opening it. Come on, that's it? After 3 seconds, I don't know. What kind of scientists are you? Maybe someday we'll have time to try this. There is something rattling in there. I think there's 12 black boxes back there. There's 6 pairs. There's 2 that are the same. And each one is different. Okay? And this is known as a black box experiment because you can't see what's inside. There is literally no answer that I can look. I've nailed them together. They're shut. I've had kids driven crazy. They want to know what's inside. I won't tell them. I had one kid once, he was so mad at me. At the end of the day, he snuck in and stole one. Took it home and opened it. And brought it back. That's a jerk. Me. I'm not telling you what's in here. That's what real science is, right? Is looking for things that you don't know. Do you ever know for sure what's in there? I have a list somewhere what's in there. Some of them are different. What if I go this way? Different that way, isn't it? Okay? That's what real science is. Not knowing for sure if you're right. You guys can look at the answers. That's a huge difference. Here it is here. You want to write this down? Okay. High school students learn about accepted theories and concepts. Doctorate students investigate new physics. They discover new things. And you can have a little bit of fun too. You can blow stuff up, right? Are the Mythbusters scientists? You guys have seen the Mythbusters, right? I know it's not on TV anymore, right? Are they doing real science action? I would agree 100%. They are indeed scientists. They have a theory, they have a question, a hypothesis. They have a hypothesis and they go and they test it. And they don't just sort of go by what people say. They actually check to see if it's right. They say that the only difference between fooling around and science is that you write the answers down in science, right? Write your results down. They have a lot of fun. I think if I had to go through life again, I think Mythbusters would be a good job. Wouldn't you? Plus they get to wear the cool hats. You guys are always this quiet. Kind of scaring me. I'll post that up for you. Let's get down to the graph and stuff. Here's where some of you are going to be challenged. Version 4, I think, is the latest. I don't think I'm going to get through this last day. Oh, I should also tell you this. Physics notes are like bananas. Why do they like bananas? Who am I going to contact? Again, why are physics notes like bananas? No idea? Come in bunches. There'll be a day when there'll be a lot of notes, and then the other days where it won't be hardly any at all. Okay? It's not going to be note practice, kind of like math, right? You know, like math, notes, here's practice questions, notes, right? There'll be some days where I'll do a lot of this, a lot of talking, and there'll be other days when I won't do any talking. Okay? So get used to it. Okay, you have this handout? Okay, so in a situation like this, what I would expect is you to sort of highlight, maybe make little notes in the margins and that kind of thing. Some of you like to do notes in a scribbler, like a wild coil scribbler. That's okay. These are going to have to go in a binder, obviously. Right? But yeah, do some highlighting. I'll do some highlighting up there as well. That would be another cue, another clue that would be something that's important. So this is really just everything you've ever learned about graphing in about 25 minutes. Okay, so after this, you'll be able to create a graph, interpret a graph, including the meaning of the slope, and that's key there. Recognize a linear, quadratic, and inverse function. If, in fact, you go back to that outline that I gave you, you will find many of those things on there. Okay, so a well-designed graph is more than a picture with 1,000 words. It can give you more information than either words, columns of numbers, or equations. To be useful, however, a graph must be drawn properly. So this, again, is just a review to make sure that you're all on the same page, have the same skill set for graphing. So in this section, we're going to develop these graphs to display data. So when driving, we're going to talk about driving because we're all really familiar with it, and it's supposed to be what you learn in grade 10. So there's two parts to the total braking distance. Remember grade 10 science. What are the two parts to the braking distance? By the way, they're right on the screen. Go ahead, what are they? Zoe? They're right there on your paper. All you got to do is read them. What are the two parts to braking distance? They are the reaction distance and the braking distance. Now, do you guys have blanks or do you have them filled in? You have blanks. Okay, so what is the reaction distance? Do you remember? Do I have it in type? No, I have to write it. What is the reaction distance? It's a distance. What is it? Anybody remember? Sarah? Do you remember from grade 10 science? You slept through grade 10 science, didn't you? Oh my God. It is the distance traveled during what? The reaction time. It's how far you go, make that a smidge smaller. It's how far you go while you're reacting, right? So as he's driving home, going out on the cliffs there, got a foot on the gas, and then all of a sudden a deer runs across the highway, and her foot has to go from gas to brake. Is she still traveling while that foot is going from gas to brake? She sure is. That distance that she travels is the reaction distance. It's how far you go while you're still reacting. What's sort of an average reaction time for people, do you think? Like what would be a ballpark appropriate number for your reaction time?
I think 1 second.
Less than a second? I would hope so, yeah. If it's more than a second, you're in trouble. You're probably texting. Don't text. What about braking distance? What is the braking distance then? Exactly. I can probably do this. Distance traveled during braking. In other words, your foot is actually on the brakes. And then, of course, the total braking distance would be what? Both of them together, added together, right, Jen? All right, good. Quick review from grade 10. Okay, so we've got a table of data here. Now, I believe yours is exactly the same. Do you have original speed in kilometers per hour? Do you have that blank? Yeah. Excellent. Okay. Do you remember the magic number, as I like to call it? It's 3.6. To go from meters per second to kilometers per hour, you're going to multiply by 3.6. Why 3.6? Do you know? Like, where does this magic number come from? Is it just kind of, well, magic? No. How many seconds in a minute? 60. How many minutes in an hour? 60. 60 times 60? 3,600. How many meters in a kilometer? So 3,600 divided by 1,000 is 3.6. This is where it comes from. So we're going from meters per second. Meters per second to kilometers per hour. Because most physics questions are going to be in meters per second, but most people only have a sort of an understanding of car speed in kilometers per hour, or maybe miles per hour, depending on your age and your experience. So go ahead. You've got 5 questions. Take 10 times 3.6. You should be able to do that in your head. It's 36. Okay, did you get that done?
Yep.
Shouldn't have taken too long. What's 15 times 3.6? 52? 54. I've done these a few times. 20? 72? 25 is 98? 90. And 30, I think, is 108. Okay, so 36 kilometers an hour. That would be like driving down a residential street. You know, like where there's houses. What's the speed limit in town? 50. Should you be doing 50 down residential streets? Probably not. Right? There's cars parked, there's kids playing, there's dogs running around, right? 54, we're talking like down, Mountain Road, right? It's a wide street. It's okay to go 50. You should be doing 50. People do a little more. 72, maybe out towards the eclipse, right? 90, maybe you're on a gravel road. 108, you're going down the Trans-Canada. So your reaction distance, if you're doing 36, down a residential street, 7.4 meters. 7.4. And I'm coming towards you. 1, 2, 3, 4, 5, 6, 7. From Anna all the way to here. That's just how far you go with your foot going from gas to brake. Before your even foot gets to the brake, that far. And then you add on another 9.1 meters for a total distance of 16.5. 16.5 would be like how far? Double that, like from Anna, from the back of the wall, all the way to into Mr. Smigowski's room and to the wall, right? That's pretty far, isn't it? That's only doing 36. One more reason you shouldn't be doing 50 down a residential street. 54 down Mountain Road, it's like 31.6 meters. That's like the length of this hallway. 51 meters, that's 72. Going down the Trans-Canada, 104 meters. That's like the length of the football field, right, Jason? Approximately. Roughly, right? That's a long way to take the break. Now, having said that, these are, is every car like this? Is every person like this? No, how come? Different cars have different weights, different braking capabilities, better brakes, worse brakes. Some people have better reaction time than others. Some people are texting. Right? Yeah. So this is just kind of an average thing. And we're really just talking about the graphic here, so we're really good. Yeah. All right. So in our example, the speed of the car is the independent variable. See what I did there? Some of you picked up on it. The independent variable. What does that mean, independent? Does it what? It doesn't depend on the other. It's sort of like, it's the thing you know, it's the thing you're changing. The speed is independent. We are graphing based on the speed. We are adjusting the speed ourselves and trying to find out what the effect is, or the manipulated variable. The other two variables, reaction distance and braking distance, change as a result of changing the speed. These quantities are called dependent variables because they depend on the independent ones. I'll give you another example. Why do you have bathroom skeletons? I just as a prop. The bigger I am, the bigger the number, right? And the more stuff that I have in my hand, the bigger the number. Right? Which one's the independent variable? My weight, or the amount of stuff I'm carrying. And the dependent variable is the number that's down there. How do distances change for a given change in speed? Notice that the reaction distance increases by about the same amount for each increase in speed. Each one of these is going up by how much? 5, exactly right. How much are these going up by, Anna? Not hard to see, right? Because it's decimals. Right? Can you tell that they're kind of going up by the same amount? You'd have to do the subtraction, right? I mean, if you did that, you'd see that it's pretty close. But if you look at the graph, here it is here. What kind of shape is the blue graph? It's a straight line, which tells you that it's going up by the same amount each time, which makes sense. If you're going faster and faster and faster, you're going to go farther and farther, right? Now, why is it a straight line? Well, just because you're going faster, right? Your reaction time is the same all the time, right? More or less. Notice the reaction distance increases by the same amount for each increase in speed. Is it easier to see that from the data, or is it easier to see it from the graph? This is an easy question. It's easier to see it from the graph. It's a straight line. That's why we graph. The braking distance, however, increases much more as the speed increases. The relationship between the distances and speed can be seen more easily if the data is plotted on the graph. Because here you can see that the braking distance, that's 9, that's up to 20, that's a difference of like 11, 16. You can tell here it's going up. But here is the red one. You can see that it's curved. Why is it curved? It's got to do with energy and a whole bunch of stuff that I'm not going to get into yet. But the faster you're going, your braking distance increases exponentially. Did they teach you that in driver's ed? You were probably asleep by that point, right?
Well, mid-key, so.
Anyways, okay. So, and then the green one here is what? What's that green line? That's the total distance. And then why is it curved? It's the sum of these two, when you add these two together, right? Did you know that a 10% increase in speed, when you're going down the Trans-Canada Highway at 100, when the speed limit is 100, and then it increases to 110, that's a 10% increase in speed, 1.1 times faster. That's actually a 21% increase in energy and a 21% increase in braking distance. 21%, that's a lot. It's kind of scary driving at 110. On some roads, right? Would you drive down, you know, the highway out to Valley River there? I don't go that way very often, but would you drive down that road at 110, the old highway? I wouldn't. Driving down the Trans-Canada, you can do it, right? You're on the freeway. Anybody been down the Anna? You're down there in LA, right? Nice wide lanes, beautiful roads. I've driven in Los Angeles doing like 140. No problem at all. How come? Wide lanes, smooth road, it's that speed, right? It's okay to drive that speed though. A little bit of throw some opinion in there. All right. How do we plot graphs? You're going to plot some graphs here right away. These are the steps. Identify the independent and dependent variables. Sometimes it's real easy. Sometimes it's not so easy. Sometimes I have to tell you. Sometimes I swap them to make the graph make sense. The independent variables plot on the horizontal or x-axis, right? Independent goes where? On the x. Dependent goes there. I often have kids say to me, which one goes on the x, Mr. Bennett? Right? It's the independent one. It's the one that you're manipulating. The dependent variable is plotted on the vertical or y. In our example, speed is plotted on the x and distance is plotted on the y. Why is speed? Oh, it's not even there. Are yours labeled? That's a bad thing. You should be labeling these, right? That should be speed. And it should be in units. Speed in meters per second. You'd almost think I did that on purpose so that I would make a point of reinforcing it. And this is going to be distance in meters. Okay, step 2. Determine the range of the independent variable to be plotted. What does range mean? Remember range and domain from math class? Everyone loves that stuff, right? Cameron, range and domain, one of your favorites? No, probably. What does range and domain mean? Anybody remember? Jacob, what's the range and domain? Remember? Lane?
Isn't that like you go on the graph, but
Sort of, yeah. You're in the right ballpark.
ranges up to down?
Yeah, that's true.
Like,
Okay, but the domain is really like one of the possible x variables, right? And the range is the possible y. Now, does that remember? Remember that now? Okay, so same thing here. When they say range here, they just mean the difference. So what is the range of the independent variable to be plotted? In our example, we started at 10 and we went to 30. Does my graph have to have 1,000 on it? No, it only has to go to 30. What's the smallest value? 10. Now, we're pretty close to 0, aren't we? Should we include 0 if we can?
Yes.
Yes. As a general rule, you should include 0 if you can. What if you can't? Have you ever seen this, where they got the graph and they can't include 0, so they kind of put a squiggly line? Have you seen that before? You can do that, although most scientists would prefer to see that 0 line, right? So if you can. Convenient range for the x-axis might be 0 to 30. Maybe even go a little bit more, in case you want to go a little bigger, right? Maybe 0 to 40. Decide if the origin is a valid data point. Now that's actually kind of key. Is the origin 0, 0 a possible data point? In our situation here, 0, 0 would be when the speed is 0. What would be the reaction distance? 0. If you're not going anywhere, you don't have any braking distance, do you, right? So is 0, 0 a valid point? Is it part of the data set? Yes, it is. Should you include it? Yes, you should. In this case, then, your graph should include the origin. Spread out the data as much as possible. Don't scrunch it down into a little teeny tiny 1-inch square at the bottom of your page, because then you can't tell any trends. Okay? Make it nice and big. Let each space in the graph paper stand for a convenient unit. You're going to have to figure that out on your own now. Choose maybe 2, 5, or 10 spaces, and so on. Number and label the horizontal axis. I say again, label. Knowing full well that kids lose marks on the upcoming test because they forget to label their graph. And repeat steps 2 to 4 for the dependent variable. Plot your data points on the graph. What does plotting mean? Just like put the data points, right? I'm hoping you can do that. Here's one where people fight me a bit. Draw the best straight line or smooth curve that passes through as many data points as possible. Do not use a series of straight line segments that connect the dots. Do not connect the dots. Anyone know why? It is not accurate, and it implies that there is data in between. Now, in this graph here, is there data in between? Is there such speed as, 11? Sure there is. Okay? Now, I have to say this. Where did this data come from? Where did you guys get these numbers from? I gave it to you. I made it up. And it's perfectly perfect. When you do graphs, when you do labs, are you going to have perfectly perfect numbers? Not even close. Connecting the dots has some sort of implication that you know what's happening in between. Your dots are not going to be like this. Your dots are going to be like this. And so you draw what's known as a line of best fit. A line that best represents the overall trend, the overall average, the overall sort of look of the data. Some nerdy professors will call that a black thread method. What they mean there is you literally get a black thread and you put it on there and you kind of go, yeah, it's about there. Okay? You can use a ruler for that, right? There is statistical tools. Your calculator likely has a stat mode on it that you have no idea how to use. And I probably don't either, but if you know how to use it, you can punch in a bunch of data and it will spit back at you the equation. If you have a graphing calculator, anybody got a graphing calculator? I got a graphing calculator, one of those old ones, they still use the math thing, don't they? The TIs. Okay? When I used to teach applied math, we used to do the graphical line of best fit as well. If you have a phone, and I'm sure you do, you can get to, Mr. Love uses it. What's that graphing program that Mr. Love uses? Desmos will tell you the equation line on it. We should do that here. We should do that here. Okay? So my point is, don't connect the dots. Draw what's known as a line of best fit or a curve of best fit. Give the graph a title that clearly tells what the graph represents. Okay? It's reaction distance versus speed or something like that. I'm giving a lot of information, and it's pretty darn boring, isn't it? I can tell by the looks on your face. Don't humor me there, Jason. I can tell by the looks on your face. Oh my God, I wish I collected at the front of the room so I could see how much longer I have to sit there. I like to call it the back because I don't stand like that. I have to speed up or slow down. Do you remember what slope is? What's the slope? How do you find slope? Remember all this stuff? All that's good math review. Let's talk about linear, quadratic, and inverse relationships. One of the outcomes is know the three relationships. Here it is. The graph, figure 2 right here, of reaction distance versus speed is a straight line. That is the dependent variable varies linearly with the independent variable. There is a linear relationship between the two variables. What's the shape of a linear relationship graph? It's a straight line, hence the name linear. The relationship of the two variables shown in this graph can be written as an equation. How many people remember y equals mx plus b? Oh, please tell me more people than that remember y equals mx plus b. Please. Thanks, Jen. What does the m stand for, Jen? Don't remember? Okay. It is the slope. The m is the slope, and the b, what's the b one called? Remember, anyone? Valerie? Might be different in French. French math, right? Oh, you didn't learn French math. Oh. Sarah? What's the B, you know? Don't know? You got it, the y-intercept. The relationship of the two variables shown in this graph can be written as an equation y equals mx plus b, where m and b are constants called the slope and y-intercept respectively. I got to do a bit of a grammar lesson here. What does the word respectively mean? It doesn't mean being nice to the person. It means units. Yeah. I saw you earlier, right? And you're just rewriting now? Okay. Oh. Okay. I think you're supposed to go with your class. Whatever. You bet. I'm thinking about it. What does the word respectively mean? It means in the same order. So when you say y equals mx plus b, where m and b are constants called the slope and y-intercept respectively, that means that the first one, which is the m, is the slope, and the b is the y-intercept. Here's an extra one here, Danny. I should get that earbud so you can hear it. Okay, that's what the word respectively means. When I say slope, I mean how steep it is, and when I say y-intercept now, we had some trouble with this. So the y-intercept is where it crosses the y-axis, where it intercepts with the y-axis. Why is that important? Because where it intercepts where the y-axis is, that is where x equals 0. And where x is equal to 0 is kind of a thing that nerds want to know. What happens when the x is 0? Sometimes it's important. And the slope m is the rise over run. Please tell me you've done rise over run. Nod, please. How many people have done rise? How many people have never heard rise over run? Never heard rise over. Really? I can't say rise over run in French. Never did slope? Okay. Okay. You're going to learn how to do slope. Here we go. To do rise over run. Rise means how much it goes up, and run means how much it goes sideways. Rise is up and down, run is sideways. How much it goes up, how much it goes. It's kind of like, who's the carpentry class? Building construction. Anyone? Nobody? Pitch of a roof? Nobody knows what pitch of a roof? Okay. Like how steep the roof is? Anna, your pitch of your roof is really high. How come? Have you been on your roof? Why not? And it's crazy steep. Have you been on my roof? No, you haven't. But it's safe. It's like this. It's like a deck up there. It's flat, right? My roof's like this, Anna's roof's like this. Okay? It's called the pitch of the roof. The slope m is the rise over the run. Okay, so the rise here. Now, how do we do this? This is a review for some, and it's a lesson for others. That's okay. Some of you guys might want to stick back and we'll practice. I might need to give you some practice stuff on rise over run. Some people. We'll see. I'll maybe make something and I'll get it to you. Okay, so I've picked two data points, 18.5 and 7.5. Okay, so I would like to insert something in there for the people that have never done this before. So slope is going to be y2 minus y1 all over x2 minus x1. And I apologize for how bad that is written. y2 minus y1 all over x2 minus x1. And what do the x's and y's stand for? Like the coordinates, right? Okay. So I'm picking these 2 points. I'm picking this point here, and I'm picking this point here. Please tell me you know how to do this. What's the coordinates of that point? 10, comma It's 7.4. How do I know it's 7.4? Because I pulled it out of right here. 10, these are the x's, these are the y's, right? 10 and 7.4. The other one is 25 and 18.5. Right? This one is at 25 and 18.5. And you know that the x comes first, right? Please tell me you know the x comes first. Sorry? You've seen that where the x comes first? Yeah. Usually we do, yeah. 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 Sure. Okay, so I've got y2 minus y1. Which one of these is the x1, y1, and which one of these is the x2, y2? Well, the x1, y1 is usually the one on the left, right? To right. Okay, so this is my y2. So 18.5 is my y2. So that's 18.5 minus 7.4. 18.5 minus 7.4. That tells me this distance. And I'm doing more here than I normally do. But that is known as the rise. How much it goes up. It's the difference between the two. And the run is this one. How much it goes here. And that's going to be 25 minus 10, which is 15. Is it coming back to you at all? A little? Oh, so you do know it. Mind me. The words. Yes, I know. I really have to learn my French words. What's it called? Oh. So it wouldn't matter if I knew it. Okay. All right. So that's good. I'm glad to hear that. Okay. So the rise is, so that difference there, 18.5 minus 7.4 is 11.1. And the run is 25 minus 10 or 15. And then you go 11.1 divided by 15. And you get a slope value of what? 0.74. 0.74. And you'll notice that there is also a unit there. 0.74 what? Seconds. Notice that the units have been kept with the variables, and the units for the slope in this situation are seconds. How did I get seconds? I asked after everyone else was done eating, I asked for seconds. Meters divided by meters per second. Meters divided by meters per second. Do you remember how to divide fractions? Do you remember that from like about grade 7 or 8? Anybody remember? You flip and multiply. Well done. So that's going to be meters times what? Seconds over meters. And then you can cancel the, and what are you left with? So the unit for the slope here is seconds, and that's important. I'm going to wager that you've never had to worry about the unit for slope before, because in math they just deal with numbers.
We did.
Did you? Good. This is kind of review. Yeah, so that's good. Go ahead, Jason.
Look at the fraction, and if they have like the same variables, we can just like eliminate them that way.
You can, but you'll notice that when you do that, like meters and meters, then you've kind of got like nothing over seconds, right? Nothing over seconds. So you
can still know that like that's.
Absolutely. If you have a basic understanding, I just sort of showed this to sort of make it clear. Okay? Yeah. So the unit for slope is seconds. Now, what does that mean? If the unit for the slope is seconds, that means that the slope is what do you measure in seconds? Time. The slope is an actual time, and that's key to physics. That's key to science, is that it's not just some number, because again, that's what they tend to do in math. I know they're trying to do better. Here, it is a time. It is, in fact, the reaction time. This poor person has a reaction time of 0.74. I think my new friend back there said it will be less than a second, right? It is the time it takes your body, takes from the instant of the message to stop the car registers in your brain, as she sees the deer, as she says, oh, I got to get stopped, deer on the road, foot from gas, foot to brake, all that takes about 0.74 seconds. Thus, the slope is a property of the system that the graph describes. It's an important thing. It's an important quantity. It is the reaction. All graphs will have, if you're actually graphing something, all graphs will have a meaning. There is a meaning to the slope. It's not just a number that they use for math to get the right answer back to book. It's 0.74. Man, I've done a lot of talking today. I apologize. It's not always going to be like this, okay? Don't worry. It's not just me going to yammer away for the next 100 days. It's not going to be like that. Some things it's got to be like this. Okay, I'm almost done. The y-intercept b is the point at which the line crosses the y-axis, and this is the y value when the value of x is 0. That's kind of important. Do you guys remember, you Frenchies, remember what y-intercept is in French? Oh, you didn't do that. Just the slope stuff. Okay. So the y-intercept is this point right here, where it crosses the y-axis, where it intercepts it. In this case, when x is 0, the value of y is 0. Well, duh. If you're not moving, your speed is 0, your reaction distance is 0. This means that when the speed is 0, so is the braking distance. The value of y does not always increase with increasing s. Sometimes the y gets smaller. And then you've got a, what kind of slope is this? Negative slope, right? When it goes down to the right, that's a negative slope. When it goes up to it, it's a slope. And that's a really big slope like Anna's roof, then the slope number is going to be big or small. When it's really steep, the slope number is big, right? And when it's flat roof like mine, it's less, small. Now, oddly enough, I don't know why the carpenters got it all wrong. Anna's roof, which is really steep, is in fact called a low-pitch roof, I think. No, sorry. It's still called a high-pitch roof, but the number is less. That's right. When it's steep like this, they use a low number, the carpenters. I don't know. Shouldn't matter because no one in here is in carpentry. What is a quadratic relationship? Do you remember the word parabola? Do we have it in French, parabola? What is a parabola? What's it look like? Big U, right? Maybe more like a bowl, sometimes really steep, right? Those are what kind of relationships? Quadratic relationships. Remember that number? And you get it when the x is squared. Right? Quadratic relationship is x squared. The graph of braking distance is not a straight line, but rather looks like a parabola. This indicates that the braking distance varies as the square of the original speed. In other words, and this is true, in other words, if you double your speed, your braking distance increases 4 times. Doubling your speed. The difference between 50 kilometers an hour and 100 is a doubling. The braking distance between 50 and 100 kilometers an hour is 4 times. It's inverse, it's squared. 2 times. What's 2 squared? 4. What if you triple your speed, Jason? What if you're doing 150 kilometers an hour on the highway? Your braking distance is increased by 3 squared? 9. 9. That's why that 1.1 increase, the 110 to 100, is an increase of 21%, because it's a quadratic relationship. Oh, I gave you this answer already. If it takes a person 40 meters to stop after driving at 50, how far will it take to stop if they're driving 100? What's the number? If it takes you 40 meters to stop after driving at 50, how far will it take to stop if driving 100? Your speed has doubled, right? The speed is 2 times, and so the braking distance is going to be not 2 times, 4 times. Someone said it. 160 meters. It's 4 times. What if you tripled? What if you were doing 150 kilometers an hour? It's going to be 9 times. 9 times 40, it's going to be 360 meters, and so on. I promise I'm almost done. Inverse relationship. Inverse relationships are when something gets big, something else gets small. I'll give you a really good example that you're familiar with. If your absence numbers go up, if you have a lot of absences, what goes down? Your mark. Marks and absences are an inverse relationship, and I can prove that. I have data for the last 10 years. I keep data on it. I graph kids' absences here at 11 physics. Guess what? What's the graph look like? As their absences go up, mark goes down. It's actually not as much related as you'd think. You expect it to be very distinct, but it's not. Okay? So that's called an inverse relationship. And it goes kind of like that. Oh my God, thank goodness I'm done. Okay, so here's a kind of review. I realize it's Friday. I realize there is only 6 minutes left. Any chance, how many questions are there? There's 4 questions. I am not an ogre. I hate giving homework, but is there any chance you could get 4 questions done for Monday? No. It'll just be us going through it, right? But you're going to have a better chance of knowing the answer if you do it real soon. Start right now, see how far you get. I'll tell you what, I'm a nice guy. Do the first 2 for Monday. First 2 for Monday.